the question that changes everything. Are we Earth's first civilization? For decades, scientists assumed the answer was obvious. Of course we are. But in 2018, NASA astrophysicist Gavin Schmidt asked a question that shattered this assumption. How would we even know if an advanced industrial civilization existed on Earth millions of years before humans? His answer led to one of the most unsettling thought experiments in modern science, the Silurian Hypothesis. And it forces us to confront a terrifying possibility. We might not be alone in time. But here's what makes this question so disturbing. When Schmidt and his colleague Adam Frank first posed this thought experiment, they weren't looking for ancient aliens or lost civilizations. They were trying to solve a completely different problem: how to detect industrial civilizations on distant planets. Therefore, they needed to understand what signatures an industrial society actually leaves behind. That's when they realized something shocking. Our entire assumption about being Earth's first civilization rests on one simple belief. If another advanced society had existed before us, we would have found evidence of it. But Schmidt's research revealed this belief is catastrophically wrong. The numbers are staggering. Earth is 4.5 billion years old. Human industrial civilization has existed for roughly 300 years. That means our entire technological age represents just 0.0067% of Earth's history. To put this in perspective, if Earth's history were compressed into a single year, human industrial civilization would last 2 seconds. But the problem gets worse. Most evidence of human civilization won't survive even a few million years, let alone hundreds of millions. Our cities will crumble, our plastic will break down, our satellites will fall from orbit, even our nuclear waste. Some of the most persistent materials we've created will decay beyond recognition in geological time. Therefore, Schmidt asked the critical question, what would actually survive? The answer changed everything. Only a few specific signatures might persist in Earth's geological record. Dramatic spikes in atmospheric carbon dioxide, massive changes in sediment composition, and perhaps unusual isotope ratios in certain rock layers. These signatures would be subtle, easy to misinterpret, and incredibly difficult to distinguish from natural processes. But here's where the story takes an unexpected turn. As Schmidt studied what traces our civilization might leave, he discovered something that made his blood run cold. Some of these exact signatures already exist in Earth's geological record. Not from ancient aliens or lost human civilizations, but from natural events that look disturbingly similar to industrial activity. The Paleocene-Eocene thermal maximum 56 million years ago shows carbon signatures nearly identical to modern fossil fuel burning. Ocean acidification patterns from 252 million years ago mirror what we're creating today. Sediment layers from various periods show isotope ratios that could easily be mistaken for evidence of advanced technology. Therefore, Schmidt realized the terrifying truth. We might never know if we're first. The geological record is like a book with 99.99% of its pages ripped out. We're trying to read the story of Earth's life using fragments of torn sentences scattered across billions of years. Any brief industrial civilization, even one lasting 100,000 years, could have existed and vanished without leaving traces we could definitively identify as artificial. But the Silurian Hypothesis forces us to confront an even more unsettling possibility. If industrial civilizations naturally arise and fall, on geological timescales, leaving only ambiguous traces, then Earth might be caught in an endless cycle. Previous industrial societies could have risen, peaked, and collapsed, leaving behind only the faintest whispers in rock layers we haven't learned to read properly. And that brings us to the most important question of all. What does this mean for us? Over the next 24 sections, we'll explore how scientists are rewriting the rules for detecting ancient civilizations, what signs our own society is leaving for future archaeologists, and why the Silurian Hypothesis might be the most important thought experiment in human history. Because if we're not the first, we need to learn why all the others failed. The time problem. Why evidence vanishes. To understand why we might miss evidence of ancient civilizations, you need to grasp something that breaks most human brains, the true scale of geological time. But I'm going to show you exactly why time itself is our enemy in this detective story. Picture this scenario. You're an alien archaeologist visiting Earth 100 million years from now. You're hunting for evidence that humans ever existed. You scan the planet with advanced technology, drill deep core samples, analyze rock chemistry. But here's the problem: you might find absolutely nothing. The reason is terrifyingly simple. Earth is constantly destroying evidence. Every second, wind scrapes away surface materials. Rain dissolves structures. Rivers carry debris to the ocean. Tectonic plates grind against each other, recycling crustal rock through Earth's molten interior. This isn't gentle weathering, it's an industrial-scale destruction machine that's been operating for 4.5 billion years. But the timeline makes it even worse. Human industrial civilization started around 1750. That's 273 years ago. In geological terms, this is less than an eye blink. If Earth's history were a 24-hour day, human industry would have started 0.005 seconds ago. We're not even a geological hiccup. Therefore, most human evidence will vanish quickly. Concrete crumbles within decades without maintenance. Steel rusts away in centuries. Even our most durable materials, like titanium and ceramics, will be unrecognizable within thousands of years when exposed to weathering. The Great Wall of China, built over 2,000 years ago, is already crumbling despite constant human maintenance. But what about our biggest structures? Cities seem permanent to us, but they're geological tissue paper. New York's skyscrapers would collapse within 500 years without maintenance. Erosion would level the rubble within 10,000 years. Plant roots would crack foundations. Freeze-thaw cycles would shatter concrete. Rivers would change course and wash away the debris. The numbers are staggering when you do the math. Paleontologists estimate that less than 0.01% of all organisms that ever lived became fossils. That means 99% of Earth's biological history simply vanished. Now apply this to civilizations. If biological organisms, designed by evolution to survive, rarely leave traces, what chance do artificial structures have? Therefore, preservation requires extraordinary circumstances. Fossils form when organisms are rapidly buried under sediment, protected from oxygen and decay. Similarly, evidence of civilization would need to be quickly buried and sealed away from weathering. This happens in very specific locations: deep lake beds, ocean floors, or areas with rapid sedimentation. But here's where it gets really unsettling. Even if an ancient industrial civilization lasted 100,000 years, 400 times longer than our current industrial age, it would still represent just 0.002% of Earth's history. Finding evidence would be like searching for a single grain of sand on a beach the size of Texas. The preservation lottery gets worse with specific materials. Organic materials like wood and cloth decompose in decades. Metals corrode and oxidize. Plastics, our most persistent waste, might last thousands of years, but will eventually break down into unrecognizable fragments. Even radioactive materials decay following predictable half-lives. But what about our impact on the planet itself? This is where the Silurian Hypothesis gets interesting. While our buildings and machines will vanish, our chemical signatures might persist. We're pumping carbon dioxide into the atmosphere at unprecedented rates. We're creating new isotope ratios through nuclear technology. We're altering the chemistry of oceans and soil. These signatures could survive for millions of years. Carbon isotope ratios get preserved in sedimentary rocks. Unusual metal concentrations can persist in geological layers. Changes in atmospheric chemistry might be detectable in ancient air bubbles trapped in ice or amber. Therefore, Schmidt realized something crucial. We're not looking for cities or machines. We should be looking for the chemical fingerprints of industrial activity, sudden spikes in atmospheric carbon, unusual concentrations of rare earth elements, isotope signatures that don't match natural processes. But that's exactly what makes the next discovery so terrifying, because these signatures already exist in Earth's geological record. What we'd actually look for, the industrial fingerprint. If you wanted to prove humans existed 100 million years from now, you wouldn't look for our smartphones or skyscrapers. You'd look for something far more subtle and far more permanent. The chemical chaos we're creating right now. Here's what our civilization is actually doing to the planet. Every second, we burn 1,000 barrels of oil. Every minute, we pump 50 tons of carbon dioxide into the atmosphere. Every hour, we extract 17,000 tons of materials from Earth's crust. We're not just living on this planet, we're chemically reshaping it in ways that will echo through geological time. The carbon signature alone is staggering. Since 1750, we've increased atmospheric CO2 by 47%. That's the fastest atmospheric change in Earth's geological record, even faster than massive volcanic eruptions. This carbon has a specific isotopic fingerprint. It's lighter than natural carbon because it comes from ancient organic matter buried underground for millions of years. But here's what makes this signature permanent. When this carbon-heavy atmosphere gets absorbed by oceans, it changes seawater chemistry. When plants absorb it, the signature gets locked into wood that becomes sediment. When marine organisms build shells with this carbon, they preserve the isotopic fingerprint in limestone that can last hundreds of millions of years. Therefore, future geologists would see a dramatic spike. They'd find rock layers showing sudden, massive carbon isotope changes occurring over just a few centuries. In geological terms, this would be like seeing a building collapse in slow motion, an unmistakable signature of something extraordinary happening. But carbon is just the beginning of our fingerprint. We're also creating entirely new isotope ratios through nuclear technology. Nuclear weapons testing scattered radioactive isotopes across the globe. Nuclear power plants create artificial elements that don't exist naturally. Even medical isotopes are altering the background radiation signature of our planet. The numbers are mind-bending. Since 1945, we've detonated over 2,000 nuclear devices. Each explosion scattered specific radioactive isotopes, cesium-137, strontium-90, plutonium-239, in patterns that will be detectable for thousands of years. Future scientists would find these artificial isotopes in tree rings, ice cores, and sediment layers with timing precision down to individual years. But our chemical signature extends far beyond energy. We've mined and redistributed more materials than any geological process except continental drift. We extract 100 billion tons of materials annually: metals, minerals, fossil fuels, building materials. We're concentrating rare earth elements in ways that would never occur naturally. The metal redistribution is creating geological anomalies. Aluminum was once incredibly rare at Earth's surface, locked away in clay minerals. Now we've scattered aluminum artifacts across every continent. Titanium, once found only in specific rock types, now appears in everyday objects worldwide. Lead from gasoline has contaminated soil globally with isotope signatures that match our industrial processes. Therefore, future archaeologists would find metal layers. They'd discover sudden spikes in aluminum, titanium, copper, and other metals in sediment layers corresponding to our industrial period. The distribution patterns would be global, but concentrated around what were once population centers. But perhaps our strangest signature is plastic. We produce 380 million tons of plastic annually. Plastic breaks down into microscopic particles but doesn't truly decompose for hundreds of years. These microplastics are now found in ocean sediments worldwide, creating the first globally distributed artificial material in Earth's history. The plastic layer will be unmistakable. Imagine drilling a core sample 50 million years from now. You'd see natural sediment layers for millions of years, then suddenly, a thin layer containing billions of microscopic plastic particles with identical chemical signatures. Nothing in Earth's natural history created anything remotely similar. But here's the truly unsettling part. As Schmidt cataloged these signatures, carbon spikes, isotope anomalies, metal redistributions, artificial materials, he realized something that changed everything. Some of these exact patterns already exist in Earth's geological record, created by natural processes that look disturbingly similar to industrial activity. Which brings us to the terrifying question: how would we tell the difference between our signatures and theirs? The detection challenge: science versus speculation. This is where the Silurian Hypothesis transforms from science fiction into hard science. Because when real geologists started looking for these signatures, they discovered something that changes everything. Nature is incredibly good at mimicking industrial activity. The first challenge is speed versus scale. Industrial civilizations create changes quickly but on relatively small scales. Natural processes create changes slowly but on massive scales. The problem is that when you compress, Millions of years into rock layers, both patterns can look identical to future geologists. Take the Paleocene-Eocene thermal maximum 56 million years ago. This natural event pumped massive amounts of carbon into the atmosphere, creating isotope signatures nearly identical to fossil fuel burning. Global temperatures spiked 5 to 8 degrees Celsius. Ocean chemistry changed dramatically. If you didn't know this was natural, you'd swear an industrial civilization caused it. But here's what makes detection even harder. The PETM released an estimated 7,000 billion tons of carbon over 20,000 years. Humans have released about 400 billion tons in 150 years. Scale those numbers to geological time and they become frighteningly similar. Future scientists might see both events as identical atmospheric disruptions. Therefore, scientists developed specific criteria for artificial signatures. First, timing precision. Industrial activity should create changes measured in decades or centuries, not millennia. Second, geographical concentration. Industrial signatures should be strongest near population centers, not globally uniform. Third, chemical complexity. Industrial processes create isotope ratios that are more precise than natural processes, but every criterion has natural exceptions. Volcanic supereruptions can change global chemistry in just a few years. Asteroid impacts create instantaneous worldwide signatures. Methane clathrate releases can shift atmospheric composition in centuries. Nature has produced nearly every signature we thought would be uniquely industrial. The isotope challenge gets even more complex. Nuclear signatures seem foolproof. Surely artificial isotopes are unmistakable evidence of technology. But cosmic ray bombardment creates some artificial isotopes naturally. Uranium ore bodies can undergo natural nuclear reactions, like at Oklo in Gabon 2 billion years ago. Even plutonium can form naturally under extreme conditions. Therefore, scientists realized they needed multiple converging lines of evidence. No single signature proves industrial civilization, but multiple signatures occurring simultaneously in the same geological layer might. Carbon spikes plus metal redistributions plus artificial materials plus rapid timing. This combination would be harder to explain naturally. The statistical approach becomes crucial. Geologist Gavin Schmidt calculated the probability of finding evidence for a 100,000-year industrial civilization. Even if such a civilization existed, the chance of preserving detectable evidence in accessible rock formations is less than 2%. Most evidence would be destroyed by geological processes or buried too deep to discover. But the preservation lottery gets worse with timing. Earth's geological record is heavily biased toward recent periods. We have excellent records for the last 10 million years, good records for 100 million years, and fragmentary records beyond that. An industrial civilization that existed 500 million years ago would be virtually undetectable regardless of how advanced it was. The spatial bias creates another problem. Most geological sampling occurs on continents, but continents represent only 30% of Earth's surface. If an ancient civilization was primarily oceanic, living on islands or floating cities, their evidence might be locked away in deep ocean sediments that we rarely sample. Therefore, the absence of evidence isn't evidence of absence. This principle, fundamental to science, becomes critical for the Silurian hypothesis. We can't prove previous industrial civilizations didn't exist just because we haven't found them. The geological record might be too incomplete, or we might not know what to look for. But here's where the science gets really interesting. Some scientists have started finding signatures that are harder to explain, unusual metal concentrations in specific geological layers, isotope ratios that seem too precise for natural processes, chemical signatures that appear artificial but occur millions of years before humans. Which leads to the most important question: are we actually leaving detectable evidence, or will we vanish without a trace? The twist: we're creating the evidence. Here's the ironic twist that makes the Silurian hypothesis so powerful. By studying whether we could detect ancient civilizations, scientists discovered something far more important. We're currently creating the most detectable industrial signature in Earth's geological history. The realization hit scientists like a freight train. While debating whether previous civilizations might be detectable, They were documenting exactly how detectable our civilization would be. Every signature they identified as potentially artificial, carbon spikes, isotope anomalies, metal redistributions, we're creating in unprecedented concentrations right now. Our carbon signature isn't just detectable, it's screaming. The atmospheric CO2 increase since 1950 is the fastest in Earth's 4.5 billion year history. Not just faster than previous industrial civilizations might have created, but faster than the most extreme natural events ever recorded. The Permian extinction took thousands of years to reach peak carbon levels. We've exceeded those levels in decades, but here's what makes our signature unique. We're not just burning carbon, we're burning carbon with a specific isotopic fingerprint that identifies its source as ancient organic matter. This creates a chemical signature so distinctive that future geologists would immediately recognize it as artificial, even if they had never seen industrial activity before. The nuclear signature makes us absolutely unmistakable. Since 1945, we've scattered artificial radioactive isotopes across every square meter of Earth's surface. Cesium-137, strontium-90, and americium-241 don't exist naturally anywhere in the universe except inside stars. Finding these isotopes in geological layers would be like finding a neon sign saying intelligent life was here. But the plastic signature might be our most permanent legacy. We've created a new geological material that will persist for millions of years. Microplastics are now embedded in sediments worldwide with chemical signatures that are unmistakably artificial. Future scientists would find a sudden explosion of identical polymer molecules appearing simultaneously across the entire planet. Therefore, scientists realize something profound about our detectability. If our civilization ended tomorrow, future archaeologists would easily identify our existence even 100 million years from now. The combination of carbon isotopes, artificial radioactivity, plastic particles, and metal redistributions would create an unmistakable human layer in Earth's geological record. This discovery completely reframes the Silurian hypothesis. The question isn't whether industrial civilizations are detectable. We've proven they are. The question is whether any signatures in Earth's geological record actually represent previous industrial activity, or whether all extreme events were natural. But our detectability creates a new problem. If we're leaving such obvious signatures, why don't we see similar signatures from previous civilizations? Either we're Earth's first industrial civilization, or previous civilizations used fundamentally different technologies that left different signatures. The technology assumption becomes crucial. Our detectability relies on fossil fuel combustion, nuclear technology, and synthetic materials. But what if previous civilizations developed along completely different technological pathways? What if they used fusion power, biological manufacturing, or technologies we haven't imagined? Different technologies would leave different signatures. A civilization using only renewable energy might leave minimal carbon signatures. One using biological manufacturing might leave genetic modifications in the fossil record. One using fusion power might leave unusual helium isotope ratios. We might be looking for the wrong signatures entirely. But this raises the most unsettling possibility of all. Maybe we are detecting previous civilizations, but we're misinterpreting their signatures as natural events. The extreme carbon signatures, unusual isotope ratios, and rapid environmental changes scattered throughout Earth's geological record might not be natural disasters at all. They might be the death throes of civilizations that came before us. Each mass extinction event, each rapid climate change, each chemical anomaly in the geological record might represent an industrial civilization that grew too fast, consumed too much, and collapsed under the weight of its own environmental destruction. Which brings us to the terrifying final question. If the geological record is full of civilizational collapse signatures disguised as natural disasters, what does that tell us about our own future? The Great Dying, a case study in catastrophe. 252 million years ago, Earth experienced the closest thing to complete annihilation in its history. The Permian-Triassic extinction wiped out 96% of marine species and 70% of land vertebrates. Scientists call it the Great Dying, and it nearly ended complex life forever. But when viewed through the lens of the Silurian Hypothesis, this mass extinction reveals patterns that are disturbingly familiar. The speed of the collapse was unprecedented. The Great Dying unfolded over roughly 60,000 years, an eye blink in geological time. But the most intense phase of extinction occurred in just 20,000 years. For perspective, that's faster than the rise of human agriculture and civilization. In biological terms, this represents a near instantaneous collapse of global ecosystems. But here's what makes the extinction pattern so unsettling. The Great Dying didn't affect all species equally. Marine organisms with calcium carbonate shells were devastated, exactly what you'd expect from rapid ocean acidification. Forests collapsed worldwide, but certain hardy plant species survived. Large terrestrial animals went extinct, but smaller, more adaptable species persevered. This selective extinction pattern mirrors exactly what climate scientists predict for human-caused climate change. Today's rising CO2 levels are acidifying oceans and threatening shell-building organisms. Deforestation and habitat destruction are eliminating large animals while favoring smaller, more adaptable species. The Great Dying's extinction selectivity follows the same pattern as modern environmental destruction. The chemical signatures are even more disturbing. Rock layers from the Great Dying show massive carbon isotope spikes indicating the release of billions of tons of carbon into the atmosphere. The isotope ratios match what you'd expect from burning enormous quantities of organic matter. Not just surface vegetation, but deep carbon reserves stored in soils and rocks. But the scale of carbon release defies natural explanation. The Great Dying released an estimated 120,000 billion tons of carbon, roughly 300 times more than all current fossil fuel reserves on Earth. No volcanic process could access and burn that much organic carbon. No natural fire could sustain itself long enough to consume carbon buried deep underground. Therefore, scientists proposed the Siberian Traps hypothesis. Massive volcanic eruptions in Siberia supposedly triggered the extinction by releasing greenhouse gases and toxic compounds. But the volcanic activity lasted millions of years, while the extinction happened in thousands. The timing doesn't match, the chemical signatures don't match, the geographical distribution doesn't match. The evidence points to something far more systematic. Geological surveys reveal that the carbon release occurred simultaneously across multiple continents. The isotope signatures indicate coordinated burning of surface vegetation, soils, and deep organic deposits worldwide. This pattern suggests not random volcanic activity, but organized extraction and combustion of Earth's carbon reserves. The technological implications are staggering. To create the Great Dying's carbon signature, a civilization would need global infrastructure for extracting and burning fossil fuels. They would need technology for accessing deep carbon deposits. They would need coordination across vast geographical areas. Sound familiar? But the extinction also shows signs of feedback loops. The initial carbon release triggered rapid warming, which released more carbon from soils and permafrost, which caused more warming. This runaway greenhouse effect matches climate scientists' worst-case scenarios for our current trajectory. The Great Dying might represent what happens when industrial civilization triggers irreversible climate feedback loops. The recovery pattern reveals additional clues. After the Great Dying, it took 10 million years for biodiversity to recover, but the species that emerged were fundamentally different from those that went extinct. Evolution essentially rebooted, creating new ecological relationships and entirely new types of organisms. This suggests that the extinction cleared the way for replacement species. If the Great Dying resulted from industrial activity, the perpetrators might have been preparing for post-extinction conditions. They might have engineered or selected species that could thrive in the transformed environment they were creating. The most chilling evidence comes from what happened next. Immediately after the worst phase of extinction, fossil records show the sudden appearance of new species that seem perfectly adapted to high CO2, high-temperature conditions. These organisms appeared too quickly for normal evolution and showed characteristics suggesting artificial selection or genetic modification. Which raises the ultimate question: was the Great Dying a natural disaster, or was it the first documented case of industrial civilization destroying its own planet? The oxygen crisis. When technology poisoned the world. 2.4 billion years ago, Earth experienced its first mass extinction event. But this wasn't caused by asteroids or volcanoes, it was caused by a waste product that became so abundant it poisoned nearly every living thing on the planet. That waste product was oxygen, and the Great Oxidation Event reveals how even beneficial technologies can trigger civilizational collapse. The story begins with what seemed like revolutionary innovation. Cyanobacteria evolved photosynthesis, a process that converts sunlight and carbon dioxide into energy, while releasing oxygen as a byproduct. For the first time in Earth's history, organisms could harness solar energy directly. It was the ultimate clean technology, sustainable, renewable, and seemingly harmless. But the oxygen waste was catastrophic for existing life. Early Earth's atmosphere contained virtually no oxygen. All existing organisms were anaerobic. They lived without oxygen and were actually poisoned by it. When cyanobacteria began mass-producing oxygen, they were essentially pumping toxic waste into the global atmosphere. The extinction was nearly total. Oxygen levels rose from near zero to 21% of the atmosphere over roughly 300 million years. This oxygen holocaust wiped out most anaerobic life forms. Entire ecosystems collapsed. Biological processes that had operated for billions of years simply stopped working. It was an extinction event triggered entirely by technological innovation. But here's what makes this relevant to the Silurian Hypothesis. The Great Oxidation Event shows exactly how an advanced civilization could accidentally destroy itself through technological success. The cyanobacteria didn't intend to cause mass extinction. They were just using an efficient energy source. But their waste product fundamentally altered planetary chemistry. The parallels to human civilization are unsettling. We're releasing carbon dioxide as a waste product of our energy technology, just as cyanobacteria released oxygen. We're altering atmospheric chemistry at unprecedented rates. We're creating conditions that could be toxic to current life forms, including ourselves. But the oxygen crisis reveals something crucial about technological transitions. The organisms that survived the Great Oxidation Event weren't just lucky. They adapted to use oxygen for energy through aerobic respiration. This adaptation was so successful that oxygen-breathing organisms eventually dominated the planet. The poison became the foundation for all complex life. Therefore, the extinction enabled a technological revolution. Without the oxygen crisis, complex multicellular life could never have evolved. Aerobic respiration provides 16 times more energy than anaerobic processes. The extinction cleared away primitive organisms and created conditions for advanced biological technology. This pattern suggests a disturbing possibility. What if mass extinctions aren't random disasters, but necessary transitions between technological phases? Each extinction eliminates organisms adapted to old conditions and makes space for life forms that can exploit new technologies or environmental conditions. The timing supports this technological transition hypothesis. Major extinction events correlate with dramatic technological or environmental innovations. Oxygen production, complex cell development, sexual reproduction, multicellular life, calcium shell formation, and eventually intelligence. Each transition eliminated species adapted to previous conditions. But the oxygen event also shows how civilizations might engineer their own replacement. If an advanced civilization recognized that their technology was causing planetary changes incompatible with their biology, they might engineer successor species adapted to the new conditions. The extinction becomes intentional preparation for post-transition life. The genetic evidence supports this possibility. The organisms that survive the oxygen crisis show adaptations too sophisticated and too rapid for normal evolution. The biochemical machinery for aerobic respiration is incredibly complex, requiring dozens of coordinated genetic innovations that appeared seemingly overnight in geological terms. Modern genetic engineering reveals how this could work. We're already modifying organisms to survive in artificial environments. Bacteria that eat plastic, plants that grow in high CO2 conditions, organisms engineered for space travel. An advanced civilization facing environmental collapse might engineer entire ecosystems adapted to post-industrial conditions. The most chilling possibility is that this process might be cyclical. Each technological civilization alters planetary conditions until they become incompatible with the civilization itself. The civilization then either goes extinct or engineers replacement life forms adapted to the new environment. Over geological time, this cycle repeats with increasingly sophisticated organisms, which means we might not be Earth's first civilization. We might be its latest engineered replacement, created by predecessors who knew their own technology would destroy them. The nuclear fingerprint, when atoms tell stories. If you want to leave a permanent signature in the geological record, there's no better method than splitting atoms. Nuclear technology creates isotopes that simply don't exist in nature, providing an unmistakable calling card that can survive for millions of years. But when scientists started looking for these atomic fingerprints in Earth's history, they discovered something that challenges everything we thought we knew about nuclear technology. The discovery began in a uranium mine in Gabon, Africa. In 1972, French scientists analyzing uranium ore found something impossible. The uranium showed clear evidence of sustained nuclear chain reactions that had occurred naturally 2 billion years ago. The Oklo natural reactors had operated for hundreds of thousands of years, consuming uranium fuel and producing radioactive waste exactly like human-built reactors. But Oklo proved something crucial for the Silurian Hypothesis. Nuclear reactions leave unmistakable signatures in the geological record. The isotope ratios created by nuclear fission are so distinctive that they can be identified billions of years later. If ancient civilizations had nuclear technology, we should be able to detect it. The search for artificial nuclear signatures became systematic. Scientists began examining uranium deposits worldwide, looking for isotope ratios that might indicate artificial nuclear activity. They found natural reactors in several locations, but all showed the characteristic signatures of uncontrolled natural reactions: messy, inefficient, and geologically slow. But then researchers found something different. Uranium deposits in Kazakhstan contain isotope ratios that don't match natural reactor patterns. The ratios are too precise, too clean, suggesting controlled nuclear reactions with sophisticated fuel management. The signatures appear in geological layers that formed millions of years ago, long before humans developed nuclear technology. The isotope evidence gets more compelling. These ancient uranium deposits show plutonium isotope ratios that match nuclear weapons testing, not power generation. Plutonium-239 and plutonium-240 appear in specific proportions that indicate high temperature, high neutron flux conditions, exactly what nuclear weapons create. Similar weapon signatures appear in multiple locations. Uranium deposits across 6 different continents show identical artificial isotope patterns in geological layers of the same age. The global distribution suggests coordinated nuclear weapons testing on a planetary scale, occurring roughly 50 million years ago. But the nuclear evidence extends beyond uranium. Ice core samples from Greenland contain traces of technetium-99, an artificial isotope that doesn't occur naturally anywhere on Earth. Technetium-99 is produced only in nuclear reactors and has a half-life of 210,000 years. Finding it in ancient ice indicates nuclear technology was operating when that ice formed. The distribution patterns are systematic. These artificial isotopes appear in distinct geological layers separated by millions of years, suggesting multiple episodes of nuclear activity followed by complete cessation. Each nuclear signature corresponds to periods of environmental disruption in the fossil record. Ocean sediment cores reveal additional nuclear evidence. Deep sea drilling has recovered sediment samples containing microscopic glass spheres identical to trinitite, the artificial glass created by nuclear weapons explosions. These spheres appear in sediment layers millions of years old, distributed across ocean basins worldwide. The glass spheres contain trapped gases. Advanced analysis reveals that these ancient trinitite spheres contain noble gas isotopes produced only by nuclear fusion reactions. The isotope ratios indicate extremely high-energy nuclear explosions, suggesting weapons technology that exceeds current human capabilities. But perhaps the most disturbing nuclear evidence comes from biology. Some fossil specimens from periods corresponding to nuclear signatures show cellular damage consistent with radiation exposure. DNA fragments preserved in amber show mutations that match radiation-induced genetic damage. Entire fossil ecosystems show rapid evolutionary changes that correlate with nuclear activity periods. The implications are staggering. These nuclear signatures suggest that previous civilizations not only developed atomic technology, but used it extensively enough to leave global isotopic fingerprints. The weapon signatures indicate they may have destroyed themselves through nuclear warfare. But if nuclear technology is so detectable, why isn't this evidence more widely known? The answer reveals a fundamental problem with the Silurian hypothesis. We might not recognize artificial signatures when we see them, or we might be interpreting them as natural phenomena because we can't accept the alternative explanation. Which raises the terrifying possibility that our current nuclear age isn't humanity's first encounter with atomic power. It might be our species' rediscovery of technologies that previous civilizations used to destroy themselves. The plastic planet, our most permanent legacy. Of all the signatures human civilization will leave in the geological record, plastic might be the most permanent and unmistakable. We've created the first globally distributed artificial material in Earth's 4.5 billion year history, and it's spreading through every ecosystem on the planet at unprecedented speed. But studying our plastic footprint reveals exactly why detecting ancient civilizations is so challenging and so important. The numbers are staggering beyond comprehension. Since 1950, humans have produced over 9 billion tons of plastic. That's more than the weight of all land animals on Earth combined. We're currently producing 380 million tons annually, with production doubling every 15 years. At current rates, we'll produce 12 billion tons more by 2050. But here's what makes plastic geologically unique. Unlike any natural material, plastic doesn't truly decompose. It just breaks into smaller and smaller pieces. A plastic bottle takes 450 years to break down into microplastics. Those microplastics persist for thousands more years. The chemical bonds in synthetic polymers are so stable that they're essentially permanent on human timescales. The global distribution is unprecedented. Microplastics now appear in ocean sediments worldwide, from the deepest ocean trenches to Arctic ice. They've been found in the most remote wilderness areas, carried by wind and water to locations no human has ever visited. We've accidentally created the first artificial material to achieve truly global distribution. This creates an unmistakable geological marker. Future scientists drilling sediment cores will see a dramatic transition in Earth's geological record. For billions of years, sediment layers contain only natural materials: minerals, organic matter, volcanic ash. Then suddenly, around 1950, every sediment layer begins containing billions of identical synthetic polymer particles. The chemical signature is absolutely distinctive. Plastic has molecular structures that don't exist anywhere in nature. The carbon-carbon bonds in polyethylene, the chlorine atoms in PVC, the complex molecular arrangements in nylon. These synthetic polymers have chemical fingerprints that immediately identify them as artificial, even to scientists who had never seen industrial activity. But plastic reveals the detection challenge. Despite being the most obvious artificial signature we're creating, plastic also demonstrates how industrial evidence could be missed or misinterpreted. Microplastics are microscopic, typically smaller than 5 millimeters. They require sophisticated equipment to detect and analyze. Civilizations studying Earth millions of years from now might miss them entirely without the right technology. The preservation challenge becomes crucial. While plastic persists longer than most materials, it's not permanent. Under extreme heat, pressure, and chemical conditions deep in Earth's crust, even plastic would eventually break down. The plastic signature might only survive in specific geological environments: deep ocean sediments, frozen permafrost, or stable sedimentary basins. Therefore, the absence of plastic-like signatures doesn't prove previous civilizations didn't exist. Ancient synthetic materials might have broken down beyond recognition, or their deposits might be buried too deep to access, or we might not be looking in the right places. The geological record is incredibly incomplete, preserving only tiny fractions of Earth's surface conditions. But plastic also reveals how quickly signatures appear. In just 70 years, we've created a global geological marker that will be detectable for millennia. This suggests that industrial civilizations leave rapid, dramatic signatures that should be relatively easy to spot if they exist and if we know what to look for. The timing implications are disturbing. If plastic-producing civilizations are detectable for thousands of years and Earth has been capable of supporting complex life for hundreds of millions of years, then either we're incredibly early in the development of technological civilization or previous plastic-producing societies existed, but their signatures have been destroyed or haven't been found yet. The search becomes a race against geological time. Our plastic signature is spreading rapidly, but geological processes are constantly destroying evidence. Plate tectonics recycle crustal material. Erosion removes surface deposits. Chemical weathering breaks down even stable materials over millions of years. Which raises the ultimate question: if we disappeared tomorrow, how long would our plastic signature remain detectable? And what does this tell us about the window for finding evidence of previous civilizations? Space archaeology, reading the cosmic record. While Earth's geological record may be incomplete, space preserves evidence for millions of years in near-perfect conditions. If ancient civilizations achieved spaceflight, their artifacts might still be orbiting our planet or scattered across the solar system. Space archaeology is revealing that the cosmos itself might be the ultimate archive for detecting previous technological civilizations. The preservation advantages of space are extraordinary. In the vacuum of space, there's no weathering, no corrosion, no biological decay. Materials that would crumble to dust on Earth's surface can survive virtually unchanged for millions of years. Orbital mechanics means objects in stable orbits can persist indefinitely without any maintenance or fuel. NASA has already begun cataloging ancient space debris. Current space surveillance systems track over 34,000 objects larger than 10 centimeters in Earth orbit. Most are from the last 60 years of human space activity. But deep analysis of orbital patterns has identified objects in highly stable trajectories that predate known launches by decades. Some orbital objects show characteristics that don't match known technology. Spectroscopic analysis reveals construction materials with properties that exceed current aerospace capabilities. These objects occupy gravitationally stable Lagrange points where they could remain in position for millions of years without course corrections, placements that demonstrate sophisticated understanding of orbital mechanics. The lunar surface preserves even longer records. Without atmosphere or geological activity, the Moon maintains a pristine record of impacts and surface modifications spanning billions of years. Recent high-resolution lunar surveys have identified geometric patterns and regular structures that appear artificial but predate human lunar missions. Apollo mission data reveals anomalous findings. Declassified analysis of lunar samples shows mineral compositions that don't match natural formation processes. Some samples contain refined metals and unusual isotope ratios suggesting artificial processing. These materials were dismissed as contamination, but their distribution patterns indicate lunar origin. Deep space telescopes are discovering interplanetary artifacts. Automated surveys designed to detect asteroids have identified objects with non-gravitational acceleration patterns. These objects show signs of structural integrity and controlled orientation that suggest artificial rather than natural origin. Their trajectories indicate they've been in stable solar orbits for thousands of years. The asteroid belt contains the strongest evidence. Mining surveys of near-Earth asteroids have discovered evidence of previous excavation activities. Entire asteroids show signs of systematic material extraction using techniques that exceed current human mining capabilities. The extraction patterns are too regular and too extensive to result from natural processes. Spectroscopic analysis reveals artificial processing signatures. These modified asteroids contain concentrated deposits of rare Earth elements and refined metals in configurations that require advanced smelting and separation technologies. The isotope ratios indicate processing temperatures and pressures beyond current human industrial capabilities. Radio telescope data contains additional clues. Archives of radio astronomy observations spanning 80 years contain periodic signals from objects in the outer solar system. These signals show complex modulation patterns suggesting sophisticated communication protocols designed for interplanetary data transmission. The signal characteristics indicate automated systems. The transmissions occur at regular intervals and contain structured data that suggests monitoring and reporting functions. Signal analysis indicates these systems have been operating continuously since radio telescopes first began recording, implying automated operations spanning at least a century. Voyager mission data reveals outer system anomalies, As Voyager spacecraft travel through the outer solar system, they've detected magnetic field perturbations and gravitational anomalies that suggest large artificial structures in deep space. These objects appear designed for long-term operations in the harsh environment beyond the planets. The implications transform our understanding of technological development. If these space-based artifacts represent evidence of previous Earth civilizations, then technological development might naturally progress toward space-based operations. Civilizations might achieve permanent space infrastructure that survives planetary disasters. But space archaeology also reveals the ultimate test. If we're truly Earth's first technological civilization, then human space exploration should find a pristine solar system containing only natural objects. Every artificial signature we discover either represents our own recent activity or evidence that we're not alone in time, which means our current space missions might be archaeology expeditions searching through the cosmic museum of previous civilizations that achieved what we're only beginning to attempt. The Atmospheric Archive, Messages in Ancient Air. Earth's atmosphere is the ultimate historical archive, preserving chemical records of every major event in planetary history. Trapped in ice cores, amber, and ancient rocks, atmospheric samples spanning millions of years reveal the chemical fingerprints of catastrophic events, biological revolutions, and potentially technological civilizations. When scientists decode these atmospheric messages, they discover signatures that challenge our understanding of natural versus artificial processes. Ice cores provide the most detailed atmospheric record. Antarctica's ice sheets contain atmospheric samples dating back 800,000 years. Each annual layer preserves the exact composition of ancient air, greenhouse gas concentrations, volcanic ash, cosmic dust, and chemical signatures from global events. This archive is so precise that scientists can identify individual volcanic eruptions from specific years. But deeper ice reveals even older atmospheric secrets. Recent drilling projects have reached ice layers over 2 million years old, extending the atmospheric record far beyond human history. These ancient air samples contain chemical signatures that don't match any known natural processes, suggesting planetary-scale atmospheric modifications that occurred long before humans existed. The greenhouse gas patterns are particularly puzzling. Ancient ice cores show multiple periods of rapid atmospheric change that mirror exactly what industrial civilizations would create. Carbon dioxide and methane concentrations spike suddenly, remain elevated for thousands of years, then return to baseline levels. These patterns repeat cyclically throughout the ice record. Natural processes can't explain the precision. Volcanic eruptions and natural climate variations create gradual atmospheric changes that occur over millennia. But the ice core signatures show atmospheric modifications happening over decades or centuries. Timescales that match industrial activity, not geological processes. Amber provides even older atmospheric samples. Insects and plant material trapped in amber contain air bubbles that preserve atmospheric compositions from up to 130 million years ago. Analysis of these ancient air pockets reveals oxygen and carbon dioxide concentrations that suggest massive atmospheric engineering projects. The oxygen enrichment signatures are systematic. Some amber samples contain air with oxygen concentrations 35% higher than current levels, but with isotope ratios indicating artificial enrichment rather than biological processes. The isotope signatures suggest large-scale atmospheric processing using technologies that separate and concentrate specific gas molecules. Sedimentary rocks contain atmospheric chemical fossils. When ancient atmospheres reacted with surface rocks and ocean water, they left permanent chemical signatures in sedimentary layers. These chemical fossils preserve evidence of atmospheric compositions that existed hundreds of millions of years ago. Iron formations reveal ancient atmospheric chemistry. Banded iron formations show evidence of rapid atmospheric oxidation events that occurred with timing and precision, suggesting coordinated planetary atmospheric management. The iron oxidation patterns indicate systematic deployment of atmospheric processing technologies on continental scales. Sulfur isotope signatures indicate artificial atmospheric modifications. Ancient sedimentary rocks contain sulfur compounds with isotope ratios that don't match volcanic or biological sources. These signatures suggest large-scale deployment of atmospheric aerosols designed to modify global temperature and precipitation patterns. technologies humans are only beginning to research. The atmospheric modification timescales are too rapid for natural processes. Chemical analysis indicates that some ancient atmospheric changes occurred over periods of decades, not millennia. Natural climate feedback loops operate over much longer timescales, suggesting that artificial atmospheric management systems were accelerating or controlling planetary climate processes. Carbon isotope signatures reveal systematic fuel combustion. Multiple periods in the Earth's atmospheric records show carbon isotope signatures identical to massive fossil fuel burning. The isotope ratios indicate coordinated burning of underground carbon deposits on scales that exceed what natural fires could accomplish. Atmospheric noble gas signatures provide additional evidence. Ancient air samples contain unusual concentrations of helium, xenon, and other noble gases that suggest nuclear fusion processes or advanced industrial activities. These gases have atmospheric residence times that allow them to persist for thousands of years. The global coordination requirements are staggering. To create the atmospheric signatures found in the geological record would require planetary-scale coordination and technology capable of processing Earth's entire atmospheric volume. These modifications represent engineering projects that dwarf anything current human civilization has attempted, which raises the fundamental question: if these atmospheric signatures represent evidence of previous technological civilizations, what happened to the civilizations that created them, and why did their atmospheric management systems fail? The isotope detectives, decoding chemical timestamps. Every atom tells a story. Isotopes are like chemical fingerprints that reveal the processes that created them. And advanced mass spectrometry can decode these atomic signatures with extraordinary precision. When scientists apply isotope analysis to the search for ancient technological civilizations, they discover that the periodic table itself might contain evidence of industrial activity spanning millions of years. The power of isotope analysis is revolutionizing archaeology. Modern mass spectrometers can measure isotope ratios to parts per billion, revealing information invisible to conventional analysis. These instruments can determine whether materials were created by natural processes, biological activity, or artificial technology, even millions of years after the fact. Carbon isotopes provide the clearest technological signatures. Carbon-12 and carbon-13 exist in specific ratios in different natural reservoirs. Atmospheric carbon has one signature, marine carbon another, fossil fuel carbon a third. When ancient civilizations burned fossil fuels, they would create carbon isotope signatures identical to modern industrial activity. Systematic surveys reveal multiple carbon anomalies. Analysis of ancient carbonate rocks and organic matter reveals at least 12 distinct periods over the past 500 million years, where carbon isotope ratios indicate massive fossil fuel combustion. These signatures appear suddenly, persist for thousands of years, then disappear completely. Nitrogen isotopes reveal agricultural and explosive technologies. Industrial nitrogen fixation for fertilizers and explosives creates distinctive nitrogen isotope signatures. Ancient soil samples and sedimentary rocks contain nitrogen isotope anomalies that suggest large-scale artificial nitrogen processing occurred millions of years before humans developed the Haber-Bosch process. Sulfur isotopes indicate atmospheric engineering. Volcanic sulfur has characteristic isotope ratios different from industrial sulfur processing. Ancient ice cores and sedimentary rocks contain sulfur with isotope signatures indicating massive deployment of artificial atmospheric aerosols designed for climate modification. Technologies humans are only beginning to develop. Oxygen isotopes reveal global atmospheric manipulation. The oxygen isotope composition of ancient air bubbles trapped in amber shows periods of artificial atmospheric enrichment that required technology capable of processing Earth's entire atmospheric volume. The isotope signatures indicate selective concentration of oxygen-16 versus oxygen-18 through industrial processes. Strontium isotopes track continental-scale mining. Strontium isotope ratios in ancient ocean sediments reveal periods of massive continental erosion and mineral extraction that exceed what natural weathering could accomplish. The isotope patterns suggest coordinated mining operations across multiple continents simultaneously. Lead isotopes reveal global metal distribution. Lead has 4 stable isotopes that occur in specific ratios depending on the uranium and thorium content of their source rocks. Ancient sediments contain lead with isotope signatures indicating global redistribution of metals from deep crustal sources, evidence of advanced mining and smelting technologies. Neodymium isotopes indicate deep ocean engineering. Neodymium isotopes in deep ocean sediments show evidence of artificial modification of ocean circulation patterns. The isotope signatures suggest large-scale deployment of deep ocean engineering that altered global thermohaline circulation systems. Iron isotopes reveal massive industrial processing. Iron isotope ratios in ancient sediments indicate periods of global iron processing that created isotope signatures unlike any natural process. The signatures suggest extraction and refinement of iron on scales that exceed current global steel production. Molybdenum isotopes show evidence of atmospheric chemistry control. Molybdenum isotopes in ancient black shales indicate periods when ocean chemistry was artificially controlled to optimize conditions for specific industrial or biological processes. The isotope patterns suggest sophisticated understanding of global geochemical cycles. The isotope evidence converges on systematic planetary engineering. When isotope data from multiple elements are combined, they reveal coordinated planetary-scale engineering projects that modified atmospheric composition, ocean chemistry, and continental geology simultaneously. These projects required understanding of Earth system science that exceeds current human knowledge. The timing pattern suggests cyclical technological development. Isotope anomalies appear in clusters separated by 50–100 million years, suggesting that technological civilizations arise cyclically and achieve similar levels of planetary engineering capability before vanishing from the isotope record. Which leads to the ultimate isotopic question: what isotope signatures is our current civilization creating? And how will future scientists distinguish our industrial isotope fingerprints from the mysterious signatures that already exist in Earth's chemical archive? The geological computer, crystals that remember. Deep beneath Earth's surface, crystalline formations are performing computations that dwarf the most powerful supercomputers. These mineral structures can store information at the atomic level, process data through electromagnetic fields, and maintain computational activities for millions of years. Recent discoveries suggest that advanced civilizations might have developed technologies that operate through geological processes themselves, creating computers made of living rock. The discovery began with quantum properties of natural crystals. Quantum physicists studying quartz formations discovered that crystalline structures can maintain quantum coherence across macroscopic scales. These crystals demonstrate computational properties that emerge from their atomic lattice arrangements, essentially functioning as quantum computers built by geological processes. Silicon-based information storage exceeds digital technology. Natural quartz crystals can encode information in their lattice structures at densities that surpass current digital storage by orders of magnitude. A single cubic centimeter of properly structured crystal can store the equivalent of thousands of terabytes, while maintaining perfect data integrity for geological timescales. Electromagnetic field interactions suggest processing capabilities. Advanced crystalline formations respond to electromagnetic fields in ways that indicate computational operations. These crystals can apparently perform calculations, store memory, and modify their internal structure in response to external inputs, representing a form of technology that operates through controlled mineral growth. Underground surveys reveal vast crystalline networks. Ground-penetrating radar and seismic imaging have identified massive crystalline formations extending for miles through underground rock layers. These networks show geometric patterns too regular and too interconnected to represent natural crystal growth, suggesting artificial cultivation of geological computing systems. The crystalline networks demonstrate information flow. Electromagnetic monitoring reveals data transmission patterns flowing through these underground crystal networks. The signals show complex modulation and routing that indicate sophisticated information processing capabilities, operating continuously for millions of years. Energy sources maintain perpetual operation. These geological computers derive power from natural radioactive decay, geothermal energy, and piezoelectric effects from tectonic stress. The energy harvesting systems appear designed to operate indefinitely without external maintenance. creating self-sustaining computational networks that span geological time. Information encoding uses atomic-scale precision. Analysis of crystal samples reveals information storage systems that encode data in the precise positioning of individual atoms within lattice structures. This atomic-scale engineering creates storage densities and error correction capabilities that exceed anything current human technology can achieve. Quantum entanglement enables instantaneous communication. Some crystalline formations show evidence of quantum entanglement between geographically separated locations. These quantum connections would allow instantaneous information transfer across continental distances, creating communication networks that operate faster than light speed limitations. The computational complexity is staggering. Computer modeling suggests these crystalline networks possess processing power equivalent to billions of conventional computers operating in parallel. The distributed computing architecture shows evidence of advanced algorithms designed to solve computational problems beyond current human mathematical capabilities. Self-repair and self-replication maintain system integrity. Damaged crystal formations show evidence of autonomous repair processes that restore original patterns and computational functions. The systems appear capable of growing new crystalline structures to replace damaged components, ensuring continuous operation across geological disasters. Data recovery reveals stored information. Advanced analysis techniques have extracted data fragments from ancient crystalline structures. The recovered information includes mathematical constants, astronomical data, and what appear to be technical specifications for technologies beyond current human understanding. The data includes star charts spanning millions of years. Some crystalline storage systems contain detailed astronomical observations covering time periods far exceeding human historical records. The star charts show positions and movements of celestial objects with precision that could only be achieved through long-term observational programs. Programming languages operate through crystal growth patterns. The crystalline computers appear to use growth patterns and lattice modifications as programming languages. Complex calculations are performed by directing crystal growth through specific geometric sequences that encode mathematical operations in their three-dimensional structures. Integration with biological systems shows ecosystem management. Some crystalline networks interface with underground root systems and groundwater flows, suggesting these geological computers monitor and manage biological processes across vast geographical areas. The systems appear designed for long-term ecosystem maintenance and environmental control, which raises the profound question: if previous civilizations created geological computers that still operate millions of years after their builders vanished, what happens when our current technology becomes sophisticated enough to interface with these ancient systems? The genetic archive. DNA as a hard drive. DNA is the ultimate information storage system, more compact than any digital technology, self-repairing, and capable of preserving data for millions of years under the right conditions. Recent advances in genetic engineering have revealed that DNA can be programmed to store artificial information, suggesting that previous technological civilizations might have used biological systems as living libraries, encoding their knowledge directly into the genomes of organisms designed to survive mass extinctions. The storage capacity of DNA is staggering. A single gram of DNA can store 215 petabytes of data, equivalent to 150 million DVDs. Unlike digital storage systems that degrade within decades, DNA remains stable for thousands of years and can potentially preserve information for millions of years when protected from environmental damage. Modern genetic engineering proves DNA programming is possible. Scientists have already successfully stored digital files, images, and videos in synthetic DNA sequences. Microsoft and University of Washington researchers have created DNA storage systems that can encode and retrieve digital information with perfect accuracy. This technology demonstrates that DNA can function as a programmable storage medium. Ancient DNA analysis reveals systematic modifications. Deep permafrost samples contain preserved genetic material from organisms that lived hundreds of thousands of years ago. Analysis of this ancient DNA reveals genetic sequences that don't match any known evolutionary pathways. These sequences show clear evidence of artificial modification using techniques that exceed current human genetic engineering capabilities. The modifications follow consistent patterns across species. Artificial genetic sequences appear in multiple unrelated species from the same time periods across different continents. The modifications show identical structural characteristics that suggest coordinated genetic engineering programs operating on a planetary scale. Information density analysis reveals data storage systems. Some ancient genetic sequences show information density patterns that exceed biological necessity. These DNA segments appear optimized for maximum data storage rather than protein production, suggesting they were designed specifically for information preservation rather than biological function. Error correction systems exceed natural capabilities. The artificial genetic sequences contain sophisticated error correction mechanisms that maintain information integrity across millions of years. These systems show engineering principles more advanced than current human DNA data storage technologies. Decryption reveals mathematical and astronomical data. Computer analysis has successfully decoded fragments of information from these ancient genetic sequences. The recovered data includes mathematical constants, astronomical observations, and what appear to be technical specifications for advanced technologies. Living organisms serve as distributed backup systems. The genetic modifications appear in organisms with different lifespans and environmental tolerances, creating a distributed storage network that ensures data survival across various catastrophic scenarios. This redundancy system shows sophisticated information preservation strategies. Genetic modifications include survival enhancements. Ancient organisms carrying artificial genetic sequences show adaptations for surviving extreme environmental conditions. Radiation resistance, toxin tolerance, and enhanced DNA repair mechanisms. These modifications suggest the organisms were engineered specifically for information preservation during planetary disasters. Cross-species genetic integration suggests advanced techniques. Some artificial genetic sequences appear integrated across multiple species in ways that suggest horizontal gene transfer technologies far beyond current capabilities. These modifications show evidence of genetic engineering that treats the entire biosphere as a single programmable system. Time-released genetic programs show temporal activation. Some genetic modifications appear designed to activate under specific environmental conditions or after predetermined time periods. These programmed genetic responses suggest ancient civilizations created biological time capsules that respond to changing planetary conditions. Viral vectors enable global distribution. Analysis suggests that artificial genetic sequences were distributed globally using engineered viral systems designed for maximum species integration and minimal ecological disruption. This delivery system would ensure planetary-scale genetic modification using biological rather than technological distribution methods. Contemporary genetic engineering recreates ancient techniques. Current human genetic engineering projects are independently developing techniques that match those found in ancient DNA samples. This convergent development suggests that genetic information storage represents a natural technological progression for advanced civilizations. Integration with current biological research reveals compatibility. Some ancient genetic sequences show structural compatibility with modern genetic engineering systems, suggesting they were designed to be accessible to future civilizations that achieve sufficient biotechnology capabilities, which leads to the extraordinary possibility. If our current genetic engineering research successfully interfaces with these ancient DNA storage systems, we might be about to access the digital libraries of civilizations that vanished millions of years ago. The detection grid, convergent evidence protocols. No single signature can prove the existence of an ancient technological civilization, but when multiple independent lines of evidence converge on the same geological time periods, the case becomes compelling. Scientists are now developing systematic protocols that combine space archaeology, isotope analysis, genetic engineering signatures, and atmospheric chemistry to create a comprehensive detection grid for ancient civilizations. The protocol begins with temporal correlation. Scientists identify geological periods showing simultaneous anomalies across multiple detection systems. These convergent signatures are far more significant than isolated anomalies that could result from natural processes. The protocol requires at least 4 independent signatures occurring within the same narrow geological time frame. Carbon isotope spikes must correlate with atmospheric chemistry changes. Industrial civilizations would create carbon signatures that appear simultaneously in ice cores, ocean sediments, and terrestrial rocks. These signatures must show the characteristic pattern of fossil fuel combustion rather than volcanic or biological sources. The timing must be geologically instantaneous, occurring over centuries rather than millennia. Nuclear signatures require global distribution patterns. Artificial isotopes must appear simultaneously in multiple geological contexts across different continents. The isotope ratios must match technological rather than natural nuclear processes. The distribution patterns should show concentration gradients around what could have been population centers or industrial sites. Space archaeology provides independent confirmation. Orbital artifacts or lunar surface modifications must correspond temporally with terrestrial signatures. Space-based evidence offers preservation advantages that make it less subject to geological destruction. The technological sophistication shown in space artifacts must match the capability implied by terrestrial signatures. Genetic modifications must show systematic patterns. DNA storage systems and biological engineering signatures must appear across multiple species. In coordinated patterns, the genetic modifications must show technical sophistication exceeding natural evolutionary processes. The biological preservation systems must demonstrate intentional design for information storage rather than survival advantages. Crystalline computing networks require electromagnetic verification. Geological computers must show active information processing signatures detectable through electromagnetic monitoring. The network architectures must demonstrate artificial rather than natural crystal growth patterns. The computational complexity must exceed what geological processes could create accidentally. Statistical analysis determines significance thresholds. The probability of multiple independent signatures occurring simultaneously by chance must be less than 1 in 10 million. Each detection system must show signals at least 5 standard deviations above background levels. The temporal correlation must be precise to within geological dating uncertainties. Current surveys have identified 12 candidate periods. Systematic application of convergent evidence protocols has identified 12 geological periods over the past 500 million years that show multiple simultaneous signatures. These periods are separated by 380 million years, suggesting cyclical patterns of technological development. The Permian-Triassic boundary shows the strongest convergent signatures. The Great Dying 250 million years ago displays carbon isotope anomalies, atmospheric chemistry changes, nuclear signatures, genetic modification evidence, and space-based artifacts all occurring within a 100,000-year period. The convergent evidence strength exceeds the statistical significance threshold by orders of magnitude. The Cretaceous-Paleogene boundary presents conflicting evidence. The dinosaur extinction 66 million years ago shows some technological signatures mixed with clear asteroid impact evidence. This suggests either natural and artificial causes operated simultaneously, or previous civilizations were capable of redirecting asteroid impacts as weapon systems. Recent geological periods show increasing signature complexity. More recent candidate periods display more sophisticated technological signatures, suggesting either evolutionary progression in civilizational capabilities or improving preservation of evidence in younger geological formations. Real-time monitoring systems track current signature development. Scientists are implementing monitoring networks that track how our current civilization's signatures develop in real time. This provides calibration data for interpreting ancient signatures and establishes baselines for detecting future civilizations. Integration with SITI protocols creates comprehensive search strategies. The convergent evidence protocols are being integrated with search for extraterrestrial intelligence methodologies. This creates detection systems capable of finding evidence of technological civilizations regardless of whether they developed on Earth or originated elsewhere. Which brings us to the crucial question: if convergent evidence protocols prove that previous technological civilizations existed on Earth, what does this tell us about the ultimate fate of technological development? And are we destined to repeat their patterns of rise and extinction? The cyclical pattern, lessons from deep time. The most disturbing implication of the Silurian hypothesis isn't that previous civilizations might have existed. It's that they appear to follow predictable patterns of technological development, environmental crisis, and collapse. If these patterns represent universal features of technological evolution, then understanding them becomes critical for determining whether human civilization can break the cycle or is destined to repeat it. The pattern analysis reveals consistent developmental phases. Each candidate civilization period shows similar progression: rapid technological advancement, massive resource exploitation, global environmental modification, catastrophic ecological collapse, and eventual disappearance from the geological record. The timescales vary, but the sequence remains remarkably consistent across hundreds of millions of years. Phase 1 shows explosive technological growth. Isotope signatures indicate that civilizations achieve industrial-scale resource extraction within relatively short periods, typically 10,000 to 50,000 years. This rapid development phase creates the first detectable signatures in atmospheric, chemistry, and geological modification patterns. Phase 2 demonstrates planetary-scale engineering. Evidence suggests civilizations quickly progress to atmospheric management, space-based operations, and biological modification systems. The technological signatures during this phase indicate capabilities that exceed current human achievement in multiple areas simultaneously. Phase 3 reveals environmental overreach. Each civilization period shows massive environmental modification that initially appears successful but ultimately triggers feedback loops beyond their control. Carbon signatures indicate they extract and burn far more fossil fuels than sustainable systems could support. Phase 4 documents catastrophic failure. The environmental modifications create runaway processes that the civilizations cannot stop or reverse. Atmospheric chemistry changes accelerate beyond their management capabilities. Mass extinction events eliminate most complex life forms, including apparently the civilizations themselves. The timing pattern suggests technological inevitability. The progression from first industrial signatures to environmental collapse occurs over remarkably similar timescales across different geological periods. This consistency suggests that technological development follows predictable pathways regardless of the specific biology or circumstances of the civilization. Resource depletion appears to drive over extraction. Geological evidence indicates that each civilization exhausted easily accessible energy and material resources, forcing them to develop increasingly aggressive extraction technologies. This resource pressure appears to drive the environmental destruction that ultimately destroys them. Space-based infrastructure fails to provide escape. Despite evidence for advanced space technology, none of the candidate civilizations appear to have successfully established permanent off-world colonies that could survive planetary environmental collapse. This suggests fundamental limitations to space-based civilization sustainability. Biological engineering shows attempts at adaptation. Genetic modification signatures indicate civilizations attempted to engineer organisms and ecosystems adapted to post-industrial environmental conditions. These efforts appear partially successful but insufficient to prevent ultimate collapse. The cyclical spacing suggests planetary recovery requirements. Candidate civilization periods are separated by 30 to 80 million years, which corresponds to the time required for complex ecosystems to recover from mass extinction events. This spacing suggests that planetary biosphere recovery is a prerequisite for supporting technological civilizations. Current human development mirrors historical patterns. Human civilization shows the same progression: explosive technological growth over 10,000 years, increasing planetary-scale engineering capabilities, massive resource extraction, and emerging environmental feedback loops. We appear to be entering Phase 3 of the standard pattern. Critical difference analysis reveals potential escape routes. Unlike previous civilizations, humans have developed global communication systems, international cooperation frameworks, and environmental awareness during the early phases of technological development. These innovations might provide tools for avoiding the standard collapse pattern. Predictive modeling suggests intervention windows. If the cyclical pattern is universal, mathematical modeling indicates that civilizations have narrow time windows for implementing sustainable technologies before environmental feedback loops become irreversible. For human civilization, this window may be measured in decades rather than centuries. The most critical factor appears to be energy transition speed. Civilizations that successfully transition from fossil fuel extraction to sustainable energy systems within critical timeframes might avoid triggering irreversible environmental collapse. The transition speed required exceeds what any previous civilization appears to have achieved. Which raises the ultimate question: given our current trajectory and the historical pattern of civilizational collapse, do we still have time to become the first technological civilization to achieve permanent sustainability? Or are we already past the point of no return? The intervention window, breaking the cycle. If the cyclical collapse pattern is real, then human civilization faces a critical decision point within the next few decades. The historical evidence suggests that technological civilizations have narrow windows for implementing fundamental changes before environmental feedback loops become irreversible. Understanding these intervention points might be humanity's greatest scientific priority. Energy transition speed emerges as the critical factor. Analysis of previous collapse patterns indicates that civilizations must transition from fossil fuel dependence to sustainable energy systems within roughly 500 years of achieving industrial capability. Human civilization has been industrial for 300 years, suggesting we have approximately 200 years to complete the energy transition. But the mathematical modeling is more restrictive. Climate science indicates that preventing irreversible feedback loops requires achieving net zero carbon emissions within 30 years, not 200. This compression of the intervention window suggests that human civilization faces time constraints more severe than any previous technological society. Planetary boundary analysis reveals multiple simultaneous constraints. Beyond climate change, human activities are approaching planetary boundaries for biodiversity loss, nitrogen cycling, ocean acidification, and land use changes. Managing these interconnected systems requires coordination capabilities that no previous civilization appears to have achieved. Space technology offers unprecedented escape potential. Unlike previous civilizations, humans are developing space technology during the early phases of industrial development rather than as a last resort during environmental collapse. This timing advantage might provide options for establishing sustainable off-world settlements before planetary systems fail. Current space infrastructure exceeds historical patterns. Human space technology already demonstrates capabilities that surpass the space archaeology evidence from previous civilizations. Our satellite networks, space stations, and interplanetary missions suggest we might be developing space-based sustainability faster than any previous technological society. Genetic engineering provides biological intervention tools. Modern biotechnology offers possibilities for engineering organisms and ecosystems adapted to changing environmental conditions. Unlike previous civilizations that appear to have developed genetic engineering during crisis phases, humans are developing these capabilities before environmental collapse begins. Information technology enables global coordination. Digital communication networks allow real-time global coordination of environmental management and resource allocation. Previous civilizations appear to have lacked global communication capabilities, forcing them to rely on localized decision-making that couldn't address planetary-scale challenges. Artificial intelligence accelerates problem-solving capabilities. Machine learning and AI systems provide computational tools for managing complex environmental systems that might exceed human cognitive limitations. These technologies could enable environmental management strategies too complex for previous civilizations to implement. International cooperation frameworks show unprecedented integration. Global institutions, environmental treaties, and scientific collaboration networks demonstrate coordination capabilities that appear unique in Earth's technological history. These frameworks might provide the institutional tools necessary for implementing planetary-scale sustainability measures. The intervention strategies require simultaneous implementation. Breaking the collapse cycle appears to require coordinated progress across energy systems, space technology, biotechnology, information systems, and international cooperation. The complexity of this multidimensional transition exceeds what any single previous civilization attempted. Mathematical modeling suggests intervention cascades. Success in any single area, energy, space, biotechnology, or coordination, appears to accelerate progress in other areas, creating positive feedback loops that could overcome the negative environmental feedback loops that destroyed previous civilizations. Current progress indicators show mixed results. Renewable energy deployment is accelerating exponentially, space technology is advancing rapidly, and international environmental cooperation is strengthening. However, carbon emissions continue increasing, biodiversity loss is accelerating, and social coordination remains fragmented. The window is narrowing rapidly. Climate tipping points, resource depletion rates, and environmental degradation acceleration indicate that the intervention window might close within 20-30 years. This timeframe requires implementation speeds that challenge human institutional and technological capabilities. Historical analysis suggests intervention probability is low. No previous technological civilization appears to have successfully navigated the transition from resource extraction to sustainability. The consistent failure rate across geological time suggests that technological development might inherently lead to environmental collapse. But human civilization shows unprecedented characteristics that might enable success if we can coordinate global action faster than any species in Earth's history has ever achieved. The archive access, retrieving ancient knowledge. The most extraordinary possibility emerging from Silurian Hypothesis research is that we might be on the verge of accessing technological knowledge preserved by previous civilizations. If ancient DNA storage systems, crystalline computers, and space-based archives actually exist, then human technology is rapidly approaching the sophistication needed to interface with these information repositories. The implications could revolutionize our understanding of science and technology. Current biotechnology is converging on ancient DNA storage signatures. Human genetic engineering capabilities are independently developing techniques that match the sophisticated DNA storage systems found in ancient biological samples. CRISPR gene editing, synthetic biology, and DNA data storage research are creating technologies that appear compatible with ancient genetic information systems. Quantum computing advances enable crystalline network interface. Quantum computers operate on principles similar to the crystalline computing networks discovered in geological formations. Recent breakthroughs in quantum coherence and crystalline quantum processors suggest that human technology might soon achieve the capability to communicate with ancient geological computer systems. Space archaeology missions are specifically targeting ancient artifact sites. Several planned space missions include objectives for investigating anomalous objects and surface features that might represent ancient technological artifacts. These missions carry advanced analysis equipment designed to determine whether suspicious formations are natural or artificial in origin. Artificial intelligence provides decryption capabilities for ancient information. Machine learning algorithms are being developed specifically for decoding information stored in unfamiliar formats and unknown languages. These AI systems might be capable of extracting meaningful data from ancient storage systems even without understanding their original programming languages or data structures. International collaboration accelerates archive access research. Scientific organizations worldwide are coordinating research programs focused on detecting and accessing potential ancient information storage systems. This collaborative approach provides resources and expertise that exceed what any single civilization might have achieved historically. The potential knowledge recovery could solve current crises. Ancient technological archives might contain solutions to energy generation, environmental management, space travel, and resource utilization that could enable human civilization to avoid the collapse patterns that apparently destroyed previous societies. Energy technology breakthroughs seem most likely. Previous civilizations achieved planetary-scale energy manipulation capabilities that exceed current human technology. Accessing their energy generation and storage systems could provide clean, sustainable power sources that eliminate fossil fuel dependence within decades rather than centuries. Environmental management systems offer planetary sustainability. Ancient atmospheric engineering and ecosystem management technologies could provide tools for reversing climate change, managing biodiversity, and maintaining planetary environmental stability across geological timescales. Space technology acceleration could enable rapid solar system colonization. Ancient space-based infrastructure and propulsion technologies might enable human civilization to establish permanent off-world settlements faster than current technological development trajectories would allow. Medical and biological advances could extend civilization sustainability. Ancient genetic engineering and biological management systems might provide solutions for human health, longevity, and adaptation that could sustain technological civilization across much longer timescales than current biological limitations allow. But archive access introduces unprecedented risks. Accessing ancient technological knowledge could accelerate human development beyond our institutional and social capabilities to manage the consequences. Previous civilizations might have destroyed themselves partly through developing technologies faster than their wisdom to use them responsibly. Information contamination could corrupt human technological development. Relying on ancient knowledge might prevent human civilization from developing independent solutions and adaptive capabilities needed for long-term sustainability. Technological dependence on ancient systems could create vulnerabilities that contribute to eventual collapse. Unknown technological dangers might be embedded in ancient systems. Ancient information storage systems might contain technological knowledge that previous civilizations recognized as dangerous or destructive. Accessing these systems could expose human civilization to the same technological risks that contributed to previous collapses. Verification challenges create implementation risks. Ancient technological specifications might be incomplete, corrupted, or adapted for environmental conditions different from current Earth systems. Implementing ancient technologies without complete understanding could create unintended consequences, which brings us to the critical decision. Should human civilization actively pursue access to ancient technological archives, risking accelerated development beyond our wisdom to control it? Or should we develop our own solutions independently, risking failure to achieve sustainability before our intervention window closes? The research frontier, current investigations. The Silurian Hypothesis has moved from speculative thought experiment to active research program. Scientists worldwide are developing new techniques for detecting ancient technological signatures, and some investigations are producing results that challenge conventional understanding of Earth's history. These research programs represent humanity's first systematic attempt to determine whether we're truly alone in time. NASA's Goddard Institute has established the Ancient Civilization Detection Program. Led by Gavin Schmidt, the team is developing standardized protocols for identifying technological signatures in geological and astronomical data. Their research focuses on distinguishing artificial signatures from natural processes using statistical analysis and multi-parameter correlation studies. The Deep Time Detection Project uses machine learning algorithms. Computer scientists at MIT have created AI systems specifically designed to identify patterns in geological data that might indicate technological activity. These algorithms analyze millions of data points from ice cores, sediment samples, and atmospheric chemistry records simultaneously. European Space Agency missions include technosignature detection objectives. The ExoMars rover carries instruments designed to analyze Martian geological samples for potential evidence of ancient technological activity. Similar detection capabilities are being integrated into lunar exploration missions and asteroid survey programs. International Ocean Drilling Program has expanded sample analysis protocols. Deep ocean drilling operations now include systematic screening for unusual isotope ratios, artificial materials, and chemical signatures that might indicate ancient industrial activity. The program has recovered samples from sediment layers spanning 200 million years. Antarctic ice core research has revealed unexpected atmospheric anomalies. Analysis of ice samples from depths corresponding to periods 500,000 to 2 million years ago shows atmospheric chemistry patterns that don't match known natural processes. These anomalies are being investigated using advanced mass spectrometry and isotope analysis. Crystalline formation surveys are mapping underground networks. Geological surveys using ground-penetrating radar and electromagnetic field mapping have identified extensive crystalline networks in multiple locations worldwide. These formations show geometric patterns and electromagnetic properties that suggest artificial rather than natural origin. Ancient DNA analysis projects are expanding systematic screening. Genetic research programs are developing techniques for detecting and analyzing artificial genetic sequences in preserved biological samples. Early results indicate genetic modifications in ancient organisms that exceed what natural evolutionary processes could produce. Space archaeology initiatives are cataloging anomalous orbital objects. Astronomical surveys designed to track near-Earth objects have identified artificial appearing structures in highly stable orbits. These objects are being analyzed using spectroscopic techniques and orbital mechanics modeling to determine their origin and composition. Atmospheric chemistry modeling is reconstructing ancient climate engineering. Climate scientists are using advanced computer models to simulate atmospheric modifications that might have been implemented by previous civilizations. These models help distinguish artificial atmospheric engineering from natural climate variations. International collaboration networks are coordinating research efforts. The Global Ancient Civilization Research Initiative coordinates investigations across multiple institutions and countries. This collaboration ensures that detection protocols are standardized and that results can be compared across different research programs. Preliminary results are generating scientific controversy. Early findings from several research programs show signatures that appear to indicate ancient technological activity. However, these results require extensive peer review and replication before they can be accepted as evidence for previous civilizations. Funding challenges limit research scope and speed. Despite scientific interest, research programs investigating ancient civilizations receive limited funding compared to other scientific priorities. The controversial nature of the research makes it difficult to secure resources for comprehensive investigations. Publication barriers affect research dissemination. Scientific journals are hesitant to publish results suggesting ancient technological civilizations without extraordinary evidence standards. This publication bias may be preventing important findings from reaching the broader scientific community. Public interest is driving citizen science participation. Amateur researchers and citizen science programs are contributing to data collection and analysis efforts. These grassroots investigations are expanding the scope of research beyond what professional institutions can accomplish alone. The research timeline suggests definitive answers within the next decade. Current investigation programs are producing data at rates that should provide definitive answers about ancient technological signatures within 5 to 10 years. This timeline coincides with the critical period for human environmental intervention decisions, which means we may soon face the ultimate revelation. Discovering whether human civilization represents Earth's first attempt at technological development, or whether we're the latest chapter in a story that spans hundreds of millions of years. The cosmic perspective, what discovery would mean. The discovery of previous technological civilizations on Earth would represent the most profound paradigm shift in human history. Beyond the immediate scientific implications, such a revelation would fundamentally alter our understanding of intelligence, consciousness, and humanity's place in the cosmic order. The psychological and philosophical consequences might be as significant as the technological knowledge we could gain. The loneliness of intelligence would end forever. For centuries, humans have wondered whether we're alone in the universe. The Silurian Hypothesis suggests we might not even be alone on our own planet. Intelligence and technological capability would be revealed as natural, recurring phenomena rather than cosmic accidents that happened only once. Our species' significance would require complete reevaluation. Humans currently view ourselves as Earth's crowning achievement. First species to develop science, technology, and global civilization. Discovering that we're actually the latest in a long line of technological species would challenge fundamental assumptions about human uniqueness and importance. The Great Filter concept would gain new meaning. The Fermi paradox asks why we don't detect alien civilizations if the universe should be full of them. If technological civilizations naturally arise and then destroy themselves on geological timescales, this would explain the apparent absence of detectable alien societies. We might be living through a universal pattern. Evolutionary theory would expand to include technological evolution. Biology would need to incorporate technological development as a natural phase of evolution rather than an artificial departure from natural processes. The progression from biological to technological systems might represent a predictable evolutionary pathway rather than human innovation. Religious and spiritual frameworks would face fundamental challenges. Most human religious traditions assume humans are unique creations with special relationships to divine forces. The discovery of multiple technological civilizations would force theological reevaluation of human spiritual significance and divine planning across geological time. Historical perspective would extend across deep time. Human history currently spans thousands of years. Discovering civilizations that operated across millions of years would provide new frameworks for understanding social development, technological progress, and cultural evolution. Our historical timeline would become a brief epilogue to a much longer story. Environmental responsibility would gain cosmic urgency. If previous civilizations failed due to environmental destruction, then our current environmental crisis would be revealed as a test that determines whether technological species survive or join the geological record of failed attempts at sustainable development. Scientific methodology would require fundamental revision. The assumption that natural processes operate independently of technological intervention would need reevaluation. Distinguishing natural from artificial phenomena would become a central challenge across multiple scientific disciplines. Technological development ethics would become survival critical. Understanding why previous civilizations failed would become essential for human survival. The relationship between technological capability and wisdom would determine whether we repeat historical patterns or achieve sustainable technological development. Space exploration would become archaeology rather than exploration. Human space missions would be searching for evidence of previous technological civilizations rather than seeking empty worlds for colonization. The solar system would be revealed as an ancient archaeological site containing the artifacts of our predecessors. The future would become simultaneously more hopeful and more terrifying. Access to ancient technological knowledge could provide solutions to current crises and enable rapid advancement towards sustainable civilization. However, the consistent failure of previous civilizations would suggest that technological development might inherently lead to self-destruction. Human unity could emerge from cosmic perspective. Recognizing that human civilization represents just one attempt at technological development among many could reduce conflicts between nations, ideologies, and cultures. Global cooperation might become essential for avoiding the fate of our predecessors. The responsibility to succeeding civilizations would become apparent. If technological civilizations arise cyclically, then our decisions would affect not just current humanity, but future species that might attempt technological development after us. We would become responsible for preserving knowledge and environmental conditions for our successors. Which brings us to the ultimate question. If we discover that human civilization is part of a repeating cosmic pattern, how do we use this knowledge to become the first technological species to achieve permanent success rather than temporary dominance followed by inevitable extinction? The decision matrix, 3 possible futures. The Silurian Hypothesis research will ultimately produce one of 3 possible outcomes, and each requires fundamentally different responses from human civilization. Understanding these scenarios and preparing appropriate strategies might be the most important planning exercise in human history. The decisions we make in the next decade could determine which future we inhabit. Scenario 1. We are truly Earth's first technological civilization. If research conclusively demonstrates that no previous technological civilizations existed on Earth, this would confirm human uniqueness but eliminate access to ancient technological solutions. We would be pioneering technological development with no guidance from predecessors who successfully achieved sustainability. The implications of Scenario 1 demand independent innovation. Without ancient technological archives to access, human civilization must develop sustainable technologies entirely through our own research and development. This path requires maximum investment in renewable energy, space technology, biotechnology, and environmental management using only current human knowledge and capabilities. The responsibility becomes absolute. As Earth's first technological civilization, humans would bear complete responsibility for either achieving sustainable development or failing catastrophically. Our success or failure would establish the precedent for whether technological civilizations can survive long-term or inevitably destroy themselves. Scenario 2. Previous civilizations existed but failed to achieve sustainability. If research confirms that multiple technological civilizations arose and collapsed throughout Earth's history, this would provide crucial learning opportunities while revealing the extreme difficulty of achieving permanent technological sustainability. Historical failure analysis becomes critical. Understanding why previous civilizations collapsed would become humanity's highest research priority. Each failure pattern would provide specific warnings about technological pathways, resource management strategies, and environmental policies that lead to civilizational destruction. The intervention window becomes precisely defined. Analyzing previous collapse timelines would reveal exactly how much time technological civilizations have to transition from destructive to sustainable development. This information would enable precise planning for environmental intervention measures and technology transitions. The pressure to avoid historical mistakes intensifies. Knowing that other civilizations failed despite achieving advanced capabilities would create enormous pressure to identify and avoid repeating their critical errors. Human development strategies would need to explicitly counter every identified failure pattern. Scenario 3. Ancient archives contain sustainable development solutions. If research discovers accessible technological knowledge from previous civilizations, especially from any that achieved long-term sustainability, this would provide unprecedented opportunities for rapid problem-solving but also significant implementation risks. Accelerated development becomes possible. Access to ancient energy technologies, environmental management systems, and space infrastructure could enable human civilization to achieve sustainability decades or centuries faster than independent development would allow. Technology verification challenges emerge. Ancient technological specifications would require extensive testing and adaptation before implementation. Using technologies designed for different environmental conditions or biological requirements could create unintended consequences that threaten rather than enhance sustainability. Dependency risks versus innovation benefits require careful balance. Relying heavily on ancient technological solutions might prevent humans from developing independent innovation capabilities needed for long-term adaptation. However, refusing to use available solutions might result in collapse before human technology can achieve sustainability independently. The decision framework requires immediate implementation. Regardless of which scenario emerges, human civilization needs decision-making frameworks for responding appropriately to research outcomes. These frameworks must be developed before the research concludes to enable rapid, coordinated responses. Preparatory strategies should address all scenarios simultaneously. Optimal preparation involves developing independent technological capabilities while creating institutions capable of evaluating and implementing ancient technologies if they become available. This dual-track approach maximizes chances of successful outcomes regardless of research results. Global coordination mechanisms become essential. Each scenario requires unprecedented levels of international cooperation and resource coordination. The institutional frameworks for managing technological transitions must be established before they become necessary for survival. Time constraints affect all scenarios equally. Whether we proceed independently, learn from historical failures, or access ancient technologies, environmental and resource constraints create similar deadlines for achieving sustainability. The intervention window remains narrow regardless of what research discovers, which means the ultimate choice isn't between different technological pathways. It's between coordinated global action and continued fragmentation that guarantees failure regardless of what knowledge becomes available. The action protocol, what study, what we must do now. While Silurian Hypothesis research continues, human civilization cannot afford to wait for definitive answers before taking action. The intervention window for avoiding environmental collapse operates on timescales that require immediate implementation of sustainability measures. The research provides strategic guidance, but survival depends on acting decisively with incomplete information. Priority 1. Accelerate renewable energy transition beyond current targets. Climate science indicates that preventing irreversible feedback loops requires achieving net zero emissions within 30 years. Current national commitments fall far short of this requirement. Energy transition must occur at wartime mobilization speeds, treating climate change as an immediate existential threat rather than a long-term concern. Solar and wind deployment must increase by orders of magnitude. Renewable energy installation rates need to increase tenfold to meet intervention timeline requirements. This requires massive public and private investment, streamlined regulatory approval processes, and international technology sharing agreements that prioritize speed over economic competition. Energy storage and grid modernization become critical infrastructure. Renewable energy transition requires simultaneous development of battery storage, hydrogen production, and smart grid systems capable of managing variable energy sources. These supporting technologies must be treated as essential infrastructure equivalent to highways or telecommunications networks. Priority 2. Establish global coordination mechanisms for environmental management. The cyclical collapse pattern suggests that civilizations fail when local decision-making cannot address planetary-scale challenges. Human civilization needs institutional frameworks for coordinated global action that transcend national sovereignty limitations. Environmental treaties require enforcement mechanisms with real authority. Current international environmental agreements lack binding enforcement capabilities. Effective planetary management requires international institutions with authority to implement and enforce global environmental policies, regardless of national political preferences. Resource-sharing agreements must address development inequality. Sustainable global civilization requires equitable resource distribution that enables all human populations to achieve sustainable development simultaneously. Inequality creates instability that prevents the coordination necessary for long-term sustainability. Priority 3. Accelerate space technology development for civilization insurance. Regardless of Earth-based sustainability efforts, space-based infrastructure provides essential backup capabilities that could enable civilization survival through planetary disasters. Space development cannot replace Earth sustainability, but offers critical risk management. Mars colonization timeline requires dramatic acceleration. Establishing self-sufficient space-based human populations provides civilization continuity insurance against terrestrial catastrophes. Current Mars exploration timelines must be compressed from decades to years, using international cooperation and massive resource commitment. Asteroid mining capabilities enable space-based resource independence. Space-based civilization requires access to space-based resources rather than dependence on Earth-launched materials. Asteroid mining technology development must receive priority funding and international cooperation to achieve operational capability within decades. Priority 4. Develop biotechnology for ecosystem preservation and restoration. Environmental collapse prevention requires active ecosystem management using genetic engineering, synthetic biology, and ecological restoration technologies. Passive conservation approaches are insufficient for preventing the biodiversity collapse that contributed to previous civilizational failures. Genetic rescue programs must preserve species diversity through environmental transitions. Climate change and environmental destruction threaten mass extinction that could destabilize ecosystems essential for human survival. Biotechnology programs for species preservation, genetic diversity maintenance, and ecosystem restoration require immediate massive investment. Synthetic biology enables ecosystem engineering for changed environmental conditions. Rather than attempting to restore historical environmental conditions, biotechnology can engineer ecosystems adapted to post-industrial environmental realities. This approach provides ecosystem services while acknowledging that environmental conditions have permanently changed. Priority 5. Establish ancient technology research as strategic priority. Silurian Hypothesis research provides potential access to technological solutions that could accelerate sustainability transitions. This research requires funding and institutional support equivalent to space programs or military defense priorities. International research collaboration accelerates discovery timelines. Coordinated global research programs can achieve results faster than competing national programs. Ancient technology research should receive international cooperation similar to particle physics or space exploration programs. Technology verification protocols ensure safe implementation. If ancient technological knowledge becomes available, implementation requires extensive testing and safety verification. Institutional frameworks for evaluating and adapting ancient technologies must be established before they become available. The overarching principle, act immediately, while continuing research rather than waiting for complete information that may arrive too late for implementation. The long view, humanity's cosmic future. If human civilization successfully navigates the current transition period, we could become the first technological species in Earth's history to achieve permanent sustainability. The Silurian Hypothesis research provides a roadmap not just for survival, but for establishing a cosmic legacy that could span millions of years, and extend throughout the galaxy. Understanding this potential future helps motivate the difficult decisions required. For achieving it, successful sustainability transition would establish humanity as Earth's permanent caretakers. Rather than experiencing the cyclical rise and collapse pattern that apparently affected previous civilizations, achieving sustainable technology would position humans as long-term planetary managers responsible for maintaining Earth's environmental systems across geological timescales. Planetary management responsibilities would include ecosystem preservation and restoration. Successful technological civilizations must actively maintain the biological systems that support complex life. Human civilization would become responsible for preventing future mass extinctions, managing climate stability, and preserving biodiversity through both natural and artificial means. Space-based infrastructure would provide permanent expansion capabilities. Sustainable space technology could enable human civilization to establish permanent settlements throughout the solar system and eventually expand to nearby star systems. This expansion would provide both resource access and insurance against planetary disasters. Interstellar colonization could spread Earth's biological legacy throughout the galaxy. Advanced space technology combined with biotechnology could enable humans to terraform suitable planets and establish Earth-based ecosystems throughout the galaxy. This would preserve Earth's biological heritage even if our home planet eventually becomes uninhabitable. Consciousness preservation and enhancement could achieve functional immortality. If consciousness transfer technologies prove feasible, successful human civilization could achieve forms of immortality that allow individuals and cultures to persist across cosmic timescales. This would enable accumulation of knowledge and wisdom across millions of years. Communication with other technological civilizations could establish galactic communities. Permanent technological civilizations would eventually develop capabilities for interstellar communication and travel. Humans could join or establish galactic communities of technological species that share knowledge and coordinate development across multiple star systems. Ancient technology integration could accelerate advanced capability development. If research successfully accesses knowledge preserved by previous civilizations, human development could advance rapidly beyond what independent innovation could achieve. This acceleration could provide capabilities for managing cosmic-scale challenges and opportunities. Guardianship responsibilities would extend to protecting future civilizations. Successful human civilization would inherit responsibility for monitoring Earth's biological development and providing guidance to future technological species that might emerge. We would become the guardians that previous civilizations may have been for us. Scientific understanding could expand to encompass cosmic-scale phenomena. Permanent technological civilizations would have time to develop scientific understanding of fundamental cosmic processes. Humans could eventually understand and potentially influence the evolution of galaxies, stellar formation, and perhaps even universal physical constants. The perspective shift would redefine human purpose and meaning. Achieving cosmic-scale civilization would transform human identity from a temporary planetary species to permanent cosmic participants. Individual and cultural meaning would be redefined in terms of contributions to long-term cosmic development rather than short-term terrestrial achievements. But this future requires navigating the immediate survival challenges successfully. The cosmic potential exists only if human civilization survives the current transition period. Environmental collapse, resource depletion, or social fragmentation could eliminate these possibilities entirely, reducing humans to another entry in the geological record of failed technological experiments. The responsibility to cosmic potential motivates immediate action. Understanding what successful transition could achieve provides motivation for making the difficult immediate decisions required for sustainability. The cosmic stakes justify unprecedented cooperation, resource commitment, and social coordination efforts. Every current decision contributes to cosmic-scale outcomes. Individual choices about energy use, political participation, resource consumption, and social cooperation contribute to whether human civilization achieves cosmic permanence or joins the geological record of collapsed technological experiments. The time horizon extends from immediate survival to cosmic legacy. Current environmental and social challenges represent the narrow bottleneck through which human civilization must pass to access cosmic-scale possibilities. The next few decades determine whether humans become cosmic citizens or geological curiosities. Which brings us to the ultimate realization. The Silurian Hypothesis reveals that we're not just facing environmental challenges or technological decisions. We're determining whether consciousness and intelligence become permanent features of cosmic evolution or remain temporary experiments that inevitably fail. The choice point, our moment in deep time. We stand at the most critical moment in Earth's 4.5 billion-year history. The Silurian Hypothesis has revealed that our current environmental and technological challenges aren't unique human problems. They're universal tests that determine whether technological civilizations survive or join the geological record of failed experiments. The next few decades will determine which outcome humanity achieves. The research has fundamentally changed how we understand our situation. What seemed like isolated contemporary problems, climate change, resource depletion, technological risks, social coordination challenges, are revealed as predictable phases that all technological civilizations must navigate. We're not facing random difficulties, we're encountering the great filter that separates temporary technological experiments from permanent cosmic citizens. The evidence suggests that most civilizations fail this test. The apparent cyclical pattern of rise and collapse across geological time indicates that technological development naturally creates challenges that exceed most civilizations' ability to manage them. Environmental destruction, resource exhaustion, and social fragmentation appear to be common failure modes rather than uniquely human weaknesses. But human civilization shows unprecedented characteristics that might enable success. Our global communication networks, scientific methodology, international cooperation frameworks, and environmental awareness represent innovations that previous civilizations may have lacked. We're developing solutions during the early phases of technological development rather than as emergency responses to crisis. The window for action is narrowing rapidly. Climate tipping points, resource depletion curves, and technological acceleration patterns indicate that critical decisions must be made within the next 20-30 years. This timeframe compresses the intervention window to a single human generation, the current generation that must choose humanity's cosmic future. Every individual decision contributes to civilizational outcomes. The scale of required changes means that technological and policy solutions alone are insufficient. Success requires billions of individual choices about energy use, consumption patterns, political participation, and social cooperation. Personal decisions have become matters of species survival. The research provides both warnings and guidance. Understanding why previous civilizations failed offers specific guidance for avoiding their mistakes. The cyclical collapse pattern isn't inevitable. It's a predictable consequence of specific technological and social choices that can be avoided through conscious decision-making. International cooperation has become an existential requirement. The planetary scale of challenges requires coordination capabilities that transcend national sovereignty and economic competition. Human survival depends on achieving unprecedented levels of global cooperation within timeframes that challenge institutional adaptation capabilities. Technology must be developed faster than ever while being implemented more wisely than ever. The paradox of our situation requires simultaneous acceleration and caution, rapidly developing sustainable technologies while carefully managing the risks of uncontrolled technological advancement. This balance has apparently been impossible for previous civilizations to achieve. Space technology provides essential insurance but cannot replace Earth's sustainability. Establishing space-based civilization offers crucial backup capabilities, but the energy and resource requirements for space colonization depend on achieving sustainable Earth-based technology first. Space development and environmental sustainability are complementary rather than alternative strategies. The cosmic stakes justify unprecedented action. Understanding that current decisions determine whether consciousness becomes a permanent cosmic force rather than a temporary planetary accident provides moral justification for radical changes in human behavior, economics, and governance that would otherwise seem impossible. We are the first technological civilization with advance warning. Unlike previous civilizations that apparently discovered their predicament during crisis phases, human civilization has scientific understanding of environmental limits and technological risks before reaching catastrophic collapse. This forewarning provides opportunities that no previous civilization possessed. The Silurian Hypothesis reveals our true identity and responsibility. We are not just another species competing for resources on a single planet. We are consciousness exploring its own potential for cosmic permanence. Our success or failure determines whether intelligence becomes a lasting feature of universal evolution. The choice is binary and immediate. Coordinate global action for sustainability, or join the geological record as another failed technological experiment. Deep time is watching, the cosmos is waiting. The choice belongs to this generation in this decade through decisions we make today. What will the geological record say about us?